welcome Dr. Stefan Fueglistaler from Princeton University as our speaker today. So I will tell you a little bit about his background. He grew up in Switzerland and did his undergraduate studies at the University at Zurich. And his undergraduate major was actually geology. He wrote a thesis on tectonic changes in Greece. And then for his doctoral work, he went to ETH in Zurich, where his doctoral thesis was about polar stratospheric clouds. So if you are not aware, I just want you to know that ETH in Zurich is one of the best, it is regarded as one of the best universities in the world. And it is definitely the best university in continental Europe by all accounts. And 21 of the graduates of ETH have received Nobel Prizes. And this includes Albert Einstein and John von Neumann. And so it's a very distinguished school. And actually, Professor Daniel Konoff also is a graduate from the same school, and he was in graduate school at the same time as Stefan Fueglistaler. And so after his PhD, Stefan came to University of Washington to work with Professor Holton. And but unfortunately, after a few months of his working with Professor Holton, Dr. Holton passed away. And so then for another year, Stefan worked with John Wallace, and then he went back for a while to ETH Zurich, and then he spent 3 years as a scientist at the University of Cambridge, and now he's a faculty member at Princeton. And he has written very, very insightful papers on a wide range of subjects, including water vapor in the atmosphere, that's the topic that he will talk about today, on cloud microphysics and stratospheric dynamics and exchange between the troposphere and the stratosphere. So let us welcome Dr. Stefan Fueglistaler.
Thank you very much for the introduction, and thank you very much for the invitation to give my talk here. As I said, I will be talking about stratospheric water vapor, and I hope that at the end of the day you will kind of both see kind of what stratospheric water vapor is all about, but that you will also see kind of the broader context of which is obviously kind of tropospheric water vapor and clouds. So before I start, I would actually like to acknowledge various collaborators over the years, and particularly for this project is Sue Liu and Tom Flanagan, PhD students from Cambridge, and Tom is working with me as a postdoc now, and Peter Haynes, who is head of department at DAM at Cambridge. Then I'd like to thank Dick Dee, who is from ISMWF, responsible for the new ISMWF era interim reanalysis, John Lanzanti from GFDL for an expert in temperature trends, and Bill Reed, Alice Ramsberg, and Larry Thomas, who have given me a lot of advice on satellite data, and Dale Hurst on in situ measurements, and Peter Bernard also ACE FTS remote sensing instrument. So I'd like to jump right in before I even give you an introduction with a motivation slide. And the motivation for this work in part comes from papers published in the late 1990s and the early 2000s, where people started looking at trends in water vapor in the stratosphere. And the stratosphere, as we will see, is actually an extremely dry place. But the people, there's very few measurements there, but people realized that there is something like a trend. And the trend is positive, it's going up. And what they also noted was that this trend is actually quite strong, and where is water vapor regulated in the stratosphere? It's actually in the tropical tropopause. We will discuss all these things. But the implication was, or the question was, is the tropical tropopause warming over the years, such that more water is coming into the stratosphere? And this is a figure from a paper that we published a few years ago, which summarizes basically what these papers did. So it was not our trend, but it summarizes what these people did. So the point is, the argument was you have over the last 50 years or so, you have a near doubling of stratospheric water vapor was the claim. But unfortunately you have no single continuous time series of a reliable instrument. What we've had is a few kind of separate instruments over given periods. And the argument at the time was simply that when you look at each instrument and record alone, they all go up. And so the idea was, okay, instead of trusting the absolute values, the idea is you probably trust more the relative progression. And in this paper, we've summarized kind of two of the key measurements, which are balloon-borne frost point hygrometer measurements. And some of these measurements were taken in the late 60s to the late 70s over Washington, D.C. And then that instrument and people moved to Boulder and did the same measurements, but with a slightly modified instrument, and they never calibrated the two instruments against each other. So you have these two populations of measurements, and the argument at the time was, okay, we can do a linear regression through this curve, and we can do a linear regression through this curve. We don't trust the absolute offset between the two because they're different instruments. But within a given instrument, you might trust the trend. So what we've done in this paper here, we've kind of pushed a little bit to visualize what it actually means when you combine the trends. Yeah? And so it means that you basically take this line, you shift it down, and you extrapolate this trend onto this trend here. So you get this black line, and this recovers what was basically at the time also in a Spark water vapor report that was summarized. And it was a normal doubling since the 1960s in terms of stratospheric water vapor. Now there's a source for methane. We've tried to sort that out. That's the light gray. And you're left with the black gray, which is kind of how much water really enters the stratosphere. And you get this increase here. And this corresponds to a temperature increase of about 4 Kelvin at the tropical tropopause. And at the time, the argument was simply, there is no indication that the tropical tropopause would have warmed by 4 Kelvin. And so the question then is, why is it going up? And that is basically kind of one of my key motivations here.
What was the motivation or the justification for shifting the earlier data down?
As said, the argument was basically that you can't trust the absolute data. But so long as you don't have a good indication that there would be a bias over the years in a given instrument, these lines would be more or less reliable. I will show, I mean that's the talk, what it's all about, but I have serious doubts about it, but one has to start somewhere. So overall, my kind of motivation is, this is a curve from spaceborne measurements, which we will see many times in my talk. This kind of water vapor going up and down since the 1990s. And my motivation is kind of, I would like to understand this curve. And what I would like to derive from this curve is, of course, on the one hand, we would like to simply derive information about the climate system. We would like to know, why is it going up here? Why is it going down here? Why is it staying on a lower level? So this is basically kind of an interpretation of past climate change, attribution to processes. On the other hand, what I would like to do is I would like to ask the question, what is the minimum number of processes that I need to consider to understand this curve? And so the questions here are basically, the TTL stands for the tropical tropopause layer. So that's that layer that controls the water. So what do we know about the dynamics? Do we need to consider the large scale, the planetary scale structure? Or do we need to consider the mesoscale? Do we have to resolve convection? Which scale do we need to understand in order to understand these variations? Of course, the other thing is cloud microphysics. Water is removed through condensate, so you must first form the condensate. And then we all know aerosol is big business these days. It's not so easy to get the kind of the removal of the water vapor. So is this curve a consequence of variations in cloud microphysics, or is it a consequence of dynamics? That is kind of the type of question I'd like to find out. And then ultimately the idea would be if we have kind of a minimum model, we could maybe derive a theory. So understanding one curve, kind of a hindcast, which might also allow you to make a forecast, to understand why these things happen. So predictive skill in that respect is the key question. And the motivation for that is that, my argument is that from a theoretical point of view, we're actually in a pretty poor position in the sense that I could not derive here on the blackboard an equation that would tell a typical free tropospheric relative humidity. Or can you derive me why the planetary albedo is 0.3? Now, these are all key elements of the climate, but they basically emerge from models. Yeah? We can't really write down and say, okay, to leading order, this must be in this regime. And so my idea is really kind of to maybe have a simpler case and learn something, and then maybe from that, learn something about a more complicated case. But my talk is basically structured along these 4 points. Kind of I give you a brief introduction of what I think interesting about water vapor and climate. I then talk about a conceptual picture of how you get rid of water, dehydration. Then I will give you some arguments why stratospheric water vapor is interesting. And then I basically show you kind of our latest results and how we derive them. So the introduction, I'm assuming you're all familiar with that. It's kind of the global energy balance, the greenhouse effect is the difference between the emitted long wave at the surface from what eventually is leaving the planet. And the key elements in this picture here are obviously the water vapor. This is the strongest greenhouse gas, and the clouds. Things like carbon dioxide are obviously very important in constraining that thing and keeping it on a certain trajectory. But these are the simple things. The complicated things are really these two things, the water vapor and the clouds, clouds, and again clouds. Yeah. That's the largest uncertainty, I would say, in our models these days. So, what is it about the water vapor? You certainly have heard that clouds are uncertain. But typically the story is, water vapor is boring because relative humidity stays constant. End of story. Well, does it? I would argue no, it's not boring at all. Consider relative humidity, which is simply the mixing ratio divided by the saturation mixing ratio, or this is just the partial pressure divided by the vapor pressure. If, and here comes the conceptual idea, we can understand the mixing ratio in a given parcel as being given by the saturation mixing ratio at some point in the past. And we note this point as x. We don't know what that is, you know? But it's clear that at some point any parcel must have been saturated. And so it's this condition at that point which are simply forward advected, and if I'm measuring here, what I see is kind of since it was the last time saturated, or you can equally say since it was actually the last time in a cloud. So basically that means you need condensate present. Since then it's passive advection. Mixing complicates your picture, but it's basically the conceptual picture is right. Yeah? And so the relative humidity is simply kind of, I relate that to the vapor pressure locally. And so I can then write this thing as simply, basically what I need to know is the mixing ratio at that saturation point, or at that point x, and I can write it as this equation, straightforward. But I can then I can plug in Clausius-Clapeyron for the vapor pressure. Yeah? So we have an expression for this thing here, that's function of temperature. And we can do the derivative of that. And this is what we get. And so this is simply the assumption Clausius-Clapeyron e exponential 1 to over t. Yeah? And you can do the derivative of that thing, so we have the change in it. And what do we get is this equation which says the fractional change of relative humidity is simply the pressure change of that point x, which comes from the division for the mixing ratio by the pressure. And you have these two temperatures. This is the local temperature. So if your local temperature goes up and down, relative humidity will change. And this is the temperature at which your parcel has been last saturated. Yeah? So this is really the controlling point here. And if we look at things in the atmosphere, there's a high correlation between temperature and pressure. And it's the dominant term is this term here, also because the vapor pressure is exponentially proportional to the temperature. So it's all driven by this temperature, more or less. What we immediately see from this equation is if the average temperature goes up, this thing does not necessarily stay constant unless Tx equals T. What does that mean? That means an atmosphere which is fully saturated. So you live in a perpetual cloud, more or less. Yeah? And only at saturation, you can rely on the fact that relative humidity stays constant. It just stays 100%. Yeah? Everything else, typically, the argument is because the average relative humidity is less than 1 or 100%, this point X is actually colder than your average temperature. And what you then immediately see is that actually as you change temperature, the system tends to go towards saturation because a given temperature change or difference gets less when you go to a higher temperature. Yeah? So for a given Tx minus T, if you keep that fixed, if you shift everything to a higher temperature, that means a smaller difference in terms of relative humidity. So that simple argument immediately shows you that it's not trivial that relative humidity stays constant. And in fact, what you see is that only a particular combination of parameters gives you constant relative humidity. So what we need to know is basically we need to understand how this point X reacts. And people have kind of come up with various scenarios, and we've mentioned kind of the Princeton theory. It all hinges on the fact that you postulate some behavior for that dehydration point X to behave in a certain fashion. And so what we would like to do is have a kind of a case in the atmosphere where we can study that. And as a little kind of motivation slide also, this is an analysis we've done for the troposphere. And we've taken the air state, and we simply wanted to know, is there actually at least an annual cycle, which is probably the statistically most robust thing that you can derive. And what we find is that within kind of the error bars from the retrieval and so on that we can estimate, we actually do find that the global mean relative humidity is not fixed. Because you have to be very careful with this instrument. There's a lot of uncertainty to it. But at least in that data set, it actually does vary over the year. And so this is just for different pressure levels. And so which is, again, kind of a point. It's not that simply because the sun is kind of going south-north, you just shift everything in a fashion such that the redistribution of clouds and dehydration points is completely symmetric. It suggests that something in the system produces some periods which are moister than others. So, what is the conceptual model or picture that we have? As said, we operate on the idea of an air parcel. And what is shown here, this thin black line is a hypothetical saturation mixing ratio line of an air parcel that is initially cooling and then warming up again. We start in this simple example with the subsaturated conditions. This might be something like 30–40% or so. As you're cooling, your mixing ratio stays constant. The saturation mixing ratio goes down. You reach 100%. If you assume that you have a nucleation barrier, it might take a while till you actually trigger nucleation. At that point, you trigger nucleation, you have the partitioning from the gas phase goes into the condensate, and as soon as you have condensate, the condensate begins to fall. And so the total mixing ratio will go down, but this line kind of is going down because you're removing water. And so at some point, you again hit this point where you have 100% relative humidity, and from there on, you're back into the subsaturated condition. This thing here is the condensate, so this is the cloud. And in this picture, there are two important things. The actual mixing ratio that you observe then later on is actually given by this point here, which is kind of from a technical perspective, this is the point of last contact with condensate. Yeah? The last time you physically modify the water budget. There's a second point, and we will evaluate things mainly around this point, which is what we call the Lagrangian dry point. But this is simply basically as you move through the atmosphere, there's somewhere a minimum point in temperature or saturation mixing ratio. And we take this as an estimator for this. The argument is simple. This is kind of two little calculations. One where we have kind of the model with a nucleation barrier, the red one, and the blue without a nucleation barrier. And when you look at things, of course, where you then have clouds, things do differ. However, in the end, what you get out, the difference is typically smaller than the differences which you need to explain. And so our argument is simply, let's start with the simple case, and we can add the cloud complication later on. So to show you why that is actually important, this is a very simple example of a flow and a temperature field. So we forget about all the cloud microphysics. What this should symbolize, and I realize, sorry, the arrows are a little bit small, but this is simple kind of a potential distribution and the flow around the potential, so the gradient wind field. And so the flow goes from left to right. This is kind of an XY plot. Twice the same flow. And this is the imposed saturation mixing ratio field. And it's in both cases exactly the same, except that we shift the phase between this and this by 180 degrees. So what do we get when air travels through this temperature field from left to the right? Along this path, through this field, and through this field. Well, here you see basically the trajectories. And as you kind of go in this direction, you're getting drier. And since we assume that kind of you remove all water in excess of saturation, there is a point here, which is kind of this Lagrangian dry point. From there on, there's no further dehydration. The water stays constant. It's just passively attracted forward. And so what you see is for the two configurations, which have exactly the same average temperature. The only thing is you shift the distribution of temperature relative to the flow field. This is a much moister atmosphere than this one. And so the point is simple. Your average temperature is not a good predictor for the water vapor field. You need to know how the flow is directed through the temperature field. So the challenge is really that we have many, many quantities from a Eulerian perspective. This is the typical way how we like to think about those atmospheric dynamics. But the controlling thing is inherently you need a Lagrangian perspective. And the question is, how do we relate the two perspectives? Perhaps as a last kind of side remark also, the problem with atmospheric water vapor, you can also say, you know, we have a lot of constraints on the water cycle, so in the intensity of the hydrological cycle. How much you actually store in the atmosphere, kind of in your reservoir, is unconstrained. Yeah? And so there's really kind of not really energetic constraints on that. So why stratospheric water vapor? Well, actually, these are observations. And I start here. This is kind of from 70 south to 70 north. This is a climatological mean distribution going from about 200 millibars to 1 millibar. So this is upper troposphere all the way up to about 40 kilometers or so in the stratosphere. And what you notice here are kind of numbers that are 6, 5, and so on. These are ppmvs, parts per million by volume. And so the stratosphere is roughly the driest place on Earth that you can imagine. And it's 4 orders of magnitude less water than here in the troposphere. So why, when you're interested in water vapor, would you go where there's no water vapor? Now, that's a good question. What I show you is kind of one reason is shown in this plot. You see the water vapor is increasing a little bit with height, but it's actually throughout this reservoir, it doesn't change very much. If you look at the same time at what methane is doing, you see kind of a mirror image. Methane is kind of large in the troposphere, and then it's getting less as you go higher up. And it turns out that you have only 3 components or constituents in the stratosphere that have a significant reservoir for hydrogen. This is molecular hydrogen, it's methane, and water vapor. If you add the water vapor and the methane, or basically take out what you seem to lose here from the methane, subtract it from this picture, you get this picture. So what that means now, it's constant. And so the story is simple. You can forget about molecular hydrogen. It's all a story about only 2 molecules. It's methane and water. And methane gets oxidized into water by OH, which leads to a contribution to water vapor, which leads to this enrichment. And the structure is basically because you have upwelling here and downwelling here. So as you travel up, methane gets oxidized, water vapor is increasing, and you're bringing kind of these moist air masses down. The fact that you go down again on this deciding branch in the mixing ratio is because of lateral mixing. So you can learn a lot about this circulation from these two plots. But for me, what is interesting is this is constant in this entire region except when you go down here. And so why is that so? Now this is because here you actually have a physical process. It's not a question between a partitioning between methane and water, but you actually have physical removal of water vapor. And so the story is simple that once we're up here, we actually, anywhere where we make a measurement, if we have methane and water, we can learn something about the controlling region. And that is a much, much simpler configuration than when you're in troposphere, when you go in Stony Brook and you're making a measurement here. You don't know where that air mass came from. You don't know what region you have to think about. Yeah? And your picture here would be very different than if I did the same thing in Princeton. Whereas here, we can all go in the same stratosphere, but you measure in the South Pole, I measure in the North Pole. We basically see the same story. And that's obviously a huge advantage. So this is another picture that illustrates that a little bit. This is now, the y-axis is in potential temperature. Trust me, this is roughly the tropopause here. And this is kind of this 100 millibar level that we've seen before, and this is as we go up. What is shown is the saturation mixing ratio. So this is not how much water you have, but it's just kind of how much you have at saturation. And so this increases dramatically, this is the color bar here, as you go into the troposphere. It increases again as you go up in the stratosphere. And this is because temperatures go up in the stratosphere because you have the ozone absorption. So this is the saturation mixing ratio field. And this is, again, the observation of water vapor. So this is the actual mixing ratio. And these are the same color codes. And so what you see is that in this picture, there's only a tiny little region here where it's sufficiently dry to explain what's going on here. And so basically the story is all air in the stratosphere up here has been processed by this tiny little region here. And that is at the tropical tropopause where you have the absolute temperature minimum. And it is actually historically, it's really interesting, this property allowed Brewer already in 1949 to derive that the basic stratospheric circulation is you have ascent across the tropical tropopause, and afterwards a global scale transport to the high latitudes. And all that Brewer did was he flew a few times in World War II. It's basically a frost point measurement in an airplane where they manually were reading off the numbers into the stratosphere of England. And the puzzle was, it was so dry over England that nowhere in your local profile of saturation mixing ratio could you reach that low saturation mixing ratio. Yeah? So that air must have been dehydrated somewhere else, and the only region in the whole planet where it's cold enough is actually the tropical tropopause here. But that's really interesting, and it can be very powerful insights from water vapor here. And that was in '49, and it took about another 4 decades till we dynamically understood that circulation. So it kind of also witness to the strength or the power that you can have in chemical trace and gas measurements. So other properties, I'd like to just show very briefly what is really interesting about stratospheric water vapor. This is a sketch. This is the troposphere, this white line is the tropopause. And we're up here in the stratosphere, and I show you measurements in 3 kind of slices of the stratosphere as function of time for the mean annual cycle. And so the first one, let's look at this one here. This is this picture here. And let's look only at H2O first. This is water. And sorry, what you see is basically now a time versus height slice. You know? And so what I've done, this is the mean profile. And these are variations over the course of a year. And these variations are vectored upwards. And the story is, you have in this controlling region here, we have an annual cycle of temperatures. It's colder in one part of the year than in the other. After that, you're in a subsaturated regime, and all what happens is passive advection of how much water has been entering at some point in the past. So what you see here is simply upward propagation of the anomalies that were imposed at this level here. And people have kind of named that also the stratospheric tape recorder signal, because kind of how much water you have is imprinted at this level. You can also do that actually if you look on this level here, and this is shown here, that this goes from South Pole to North Pole. This is the equator, and so these low values here, you see them also propagating laterally. Yeah? And so what you basically see in this picture here is, because you have a modulation of the conditions here, you see the transport in the stratosphere going up, and you see an outmixing horizontally in it. And so that's a very powerful thing. So what we see here is, again, kind of I can make a measurement up here, and I can learn something about temporal variation down here. The same is actually true also for interannual variability. And this is now just, again, the height versus time plot after taking out the mean annual cycle. So I'm taking out the seasonality. And you see the same type of variability going up. And it's basically this kind of picture that I would like to understand now. So the region we're interested in, this is kind of a latitude height plot, is basically this region here, which has also been called the tropical tropopause layer. And the peculiar thing about this thing is it's a transition from the thermally direct tropospheric circulation to the stratospheric circulation. So what's different about that? In the troposphere, your air is always above radiative equilibrium temperature. You're in a constant state of radiative cooling. Air is subsiding. The energy supplied for that subsidence comes from the latent heat release primarily. And this is what is shown here. The colored filled lines are the radiative cooling rates. And the thin lines are the heating that you get from latent heat release. Yeah? So the troposphere is in a state where you have subsidence everywhere, and you replace the energy by the latent heat release. This is fundamentally different in the stratosphere. The stratosphere is in the global average, is in radiative equilibrium. There is no heat source from latent heat. However, you have a dynamically forced circulation such that part of the stratosphere is below radiative equilibrium, air goes up, and the part is above radiative equilibrium, air goes diabatically down. And the controlling region here is exactly this transition in the circulation. So what is interesting about the temporal variation in this region here is obviously there's this annual cycle which we have seen, but also the interannual variability, and this is a bit a complicated plot. Let me try mostly describe it with words. So you have temperature fluctuations that influence the water vapor. If that is kind of randomly fluctuating, it's very difficult to predict what it would do on the water vapor. In this layer, we have a nice advantage. There's the so-called stratospheric quasi-biennial oscillation. That's a 2-year oscillation that's propagating down. What that thing is actually zonally very symmetric. That means that all temperatures in this layer, they're either a little bit higher or a little bit lower. But there's very little spatial structure in it. The second thing is this residual circulation is also symmetric about the equator, so it's zonally very, very symmetric. Again, you have not large spatial structure in it. So you have two processes which basically just make this layer a bit colder or a bit warmer throughout the whole layer. Whereas there's a third process, which is El Niño, which imposes a zonally asymmetric signal. Some regions of this layer will cool and others will warm. And these three processes are the main drivers of variability. And that's nice, because you have two which are zonally symmetric, where everything does the same thing, and you have one where just one region gets warmer and the other gets colder. So why is that important? This is the temperature minimum at the tropopause. And what you see is that even though it's in a zonal mean sense, this is now longitude versus latitude of the tropics. What you see, this is the saturation mixing ratio. it actually, even within the inner tropics, it varies by a factor 10. And that comes from the quasi-stationary temperature structure. And so you immediately see that if all air were to enter the stratosphere in this part, going up, it would be 10 times moister, drier, so then everything would come up here. And so the question is, as you travel up, what is your probability to kind of experience a temperature in this region of minimum temperature? And again, we can only answer that when you do kind of the full Lagrangian calculation. So how do we do that? That's right, what we basically need, what we want to do is we kind of want to understand water vapor up here, so we need measurements up here. We need the temperatures here, and we need the transport up here. We do that with trajectories that we calculate with ECMWF winds. So we have a metric for the transport going from here to here, and we have along these trajectories, we have the temperature histories. And from that, we predict how much water goes in. So this is schematically shown here, so we have a lot of trajectories going up. And we do two things. One is we estimate trajectories here. So we start them on just a little bit above the minimum temperature level. We trace them back. And every trajectory somewhere has a Lagrangian dry point. Remember, this was this picture here. And so we estimate the moisture here based on the minimum temperature here. And from that, we have a metric for the entry mixing ratios. We want to compare with more data, so we actually also want to compare higher up, and there's a reason for that. One is the measurements around here may be contaminated by aerosol, so that's particularly true for the extinction measurements, which is less of a problem up here. And so we would basically like to relate what we have here to what we have up here. And we do that actually with basically using a stratospheric H spectrum, so we use a very idealized representation of transport. The reason why we're not calculating trajectories from here is if we do that, we add an additional uncertainty, namely how good is the model in basically reproducing stratospheric transport. Yeah? So we don't want to have this additional uncertainty.
What's your time scale?
Exactly. So the time scale would be to go from here to here, it's roughly 1.5 years. To go from here to here, we're talking about weeks to months. Yeah? So even here, you can have a lot of reservations whether that is actually a meaningful thing. We treat it basically from a statistical point of view. There's a lot of problems to it. Yeah? I'm not denying that. But assuming first that this would give a sensible statistical estimate of what you typically experience as you travel up. So I'll skip this one. I just want to briefly say the problem up here is obviously this methane contribution. And we need to estimate how much water what we observe here comes from methane. If we have a measurement that measures methane, that's relatively straightforward. But many measurements that we have are only water vapor. So when we compare our model estimates, we need to add the methane thing. And what we've noted is simply that if you calculate the fraction of oxidized methane up here, so not the absolute amount of methane, but what is the ratio of how much methane comes in here to what you have up here. This is almost constant over time. So methane goes up in the troposphere, but roughly the same fraction is oxidized. And this is shown in this plot, but just believe me, this is the fraction of oxidized methane since the 1990s based on HALO, which is one measurement. And you see fluctuations, but it actually has a remarkably little trend over these 15 years or so, which is interesting in itself, because methane is kind of an age tracer. So how much you oxidize depends on how long you're in the stratosphere. And what this plot suggests is that over these 15 years, they have not much changed. Well, all that has changed is how much goes into, because you have more methane in the troposphere. So one of the results that we published a few years ago is, when we now ask, where are these Lagrangian dry points? We can draw a map of the density distribution. And what this is, the color is the temperature that they experience. And these black lines, which are a bit hard to see, are the density distributions. And so what you should see, particularly here, is that the coldest regions are also those that have the highest frequency of these Lagrangian dry points. So that means you can basically predict how much water enters by multiplying this temperature field with the density distribution or the weighting function provided by this density distribution. So that simply means if you do a plain average temperature, you're completely off. Yeah? You need to weight that kind of minimum temperature more than the warm temperatures. So does that make sense? Yes, it does, because again, remember, we're not interested in the Eulerian perspective. You're interested in as things travel around. And eventually, what will the parcel remember is not the average temperature. It will remember only the minimum temperature. And so if you have a region which is on average colder than the surrounding region, and the parcel travels into that region and comes out again, it will remember the conditions at that point in that region. You know? And it's actually the difficulty to predict this distribution that prevents us from making a statement basically from just area average temperatures. So we can make the same case for the time, and I'm running out of time, so I have to speed up a little bit. But what this shows is simply this is time, and we have here two release points, and this is height, and this is roughly the tropical tropopause level. And each point here is a Lagrangian dry point of the trajectory is launched here and traced back in time at 2 seasons. And again, what you see is down here we have the density distribution over time. And so when you ask air at 80 millibars, kind of in February, where have you been last dehydrated and when? It actually turns out that it has not been so long ago, maybe a few weeks. Whereas if you do the same question in kind of late summer, the distribution is very wide. Again, we can understand that if you have a relatively slow mixing or transport, and what you see, the absolute temperature minimum, and this is this annual cycle, it's much colder here than here. So any air mass that is hanging around for a few weeks, even if you observe it at some point here, there's a probability that it has been in the past here. And so it will not be remoistened since then. And this is why this distribution is much wider than this one here. It shows you another problem that as you go over time, you cannot assume that basically your age distribution or time since last dehydration stays constant in time. Yeah? It also evolves with the temperature evolution of the atmosphere. So what we eventually want to do, is, as I said, is kind of trends. And the problem is we have an uncertainty in the observational data. And so what I do for the rest of the talk is I basically talk about we use a whole set of temperature sets. We use basically only one transport for which we calculate the directives from ECMWF data, but we substitute the temperature field with other temperature fields. And what we use here, this is both the era interim data. We use MERA, which is another reanalysis. We use CFSR, which is a new NSET product. We use the RATPAC homogenized radiosonde data, the HADAT2, and the RICH version 1.5 data. So these are three efforts to homogenize the radiosonde record. And just to give you an idea how different they are, this is pressure, again, tropical cold point region here. This is the temperature distribution in summer, Eulerian mean. This is in winter, this is annual mean according to era interim. And what this gray shaded region is roughly where 90% of the Lagrangian dry points happen. So for the stratospheric water vapor, we're interested in what's happening in this gray region. This is the linear trends from different data sets. Yeah? And you see you have some data sets which are warming and some which are cooling, exactly in that region that we're interested. So this is the uncertainty that we have to bracket. And this is why we substitute these temperature data. There's another picture. Look at just this one. This is 100 millibar. The black line is the difference between era interim data and the input radiosonde data that they use to derive the reanalysis. So this is relatively stable over time. It has a bump here. We have identified what that is. that is when they introduced cosmic GPS temperature data. And what that did, because you have so many observations from that basically shifted the whole analysis system to a new state. And that is happening at the end of 2006. For the rest, it seems relatively stable. However, when you calculate what is the difference to MERA, for example, you see that particularly in the 80s, we can just have about everything. Well, I don't know what MERA is doing. I don't know what CFSR is doing. But it's very clear that they all do something different in the 80s. Another problem here, this is an effort to, based on the Haddad-2, so you shouldn't necessarily trust homogenized radiosonde data either, but this shows is the difference between era interim and the radiosonde at the positions of the radiosondes. And what I've done is I've averaged them in latitude between 10 or 15 south north, and I had a kind of a Gaussian kernel in longitude to produce kind of a Hofmöller type diagram. And so what happens is, particularly in this sector, this is the Eastern Pacific sector, there's only 2 stations actually there. And this is where you see the largest drifts. This is the average difference. Again, you see this one here. This is the drop when ECMWF did something different. But you also see, for example, this one here, where just 2, or kind of the entire Eastern Pacific, which is just that, 2 stations, all of a sudden decide to go, much colder. And in this specific case, I would tend probably more to reanalysis than the homogenization effort. But the bottom line is, the temperature correction is also not spatially uniform. So it's a big problem. This is the quasi-stationary temperature field difference between era interim. This is the temperature field in January, this is in July. These are the differences to MERA and differences to the CFSR. The scale here goes plus minus 2 Kelvin. So simply kind of what is the quasi-stationary structure is also quite different. So what we've done is basically, now to fast forward, what we've done is we've taken the transport, but we've substituted basically the quasi-stationary monthly mean fields from different temperature data sets. And with that, I get kind of an uncertainty that I have in the predicted water vapor based on just the temperature uncertainty. And so the result is something like this. Let's look first at the mean annual cycle. And what we find, if you plot it as function of temperature, of the mean versus the peak to peak, so that's the mean annual cycle. Our estimate is here. These colored points here are for each longitude, latitude grid box that I have in ECMWF data. The mean and the peak to peak annual cycle of the monthly mean data. Yeah? And so what you see is that this is the tropics. So if you pick any particular point, you can just get anything what you want. Yeah? You can get any mean to amplitude combination. However, the Lagrangian estimate is substantially drier than any point that is kind of in the monthly mean data. And what that says is obviously it's the strong weighting of the very coldest positions, but it also says there's a strong weighting to times when you're anomalously cold. And that's primarily temporal variability on the sub-monthly scale, so from waves, for example, yeah, which are not in a monthly mean captured. If we compare these points to what we have observed in water vapor, we are, and there's a lot of points here, just focus on these 2 black ones. That's one measurement of water vapor. That's another measurement of water vapor. They supposedly measure the same thing. We see it's not the same thing. Huh? One is much drier than the other, but also this guy's amplitude is actually much larger than this guy's. Our estimates are down here, but they're substantially dry biased. And we've made some model calculation, and it's a very complicated figure. Take my word for it. What you want to do is basically you have temporal variability. So now you have an error in your temporal variability of the temperature. How does that affect your Lagrangian estimate? It's a non-trivial question. And the basic bottom line is this. If you have an error in the variance, so simply the fluctuations of temperature, this translates into an error of the mean of the Lagrangian estimate, because the Lagrangian estimate is sampling only the coldest times. So it doesn't care so much about the mean, it also cares about the mean, but it also cares about the spread that you have. And so if a data set, for example, has an error in the variance, you also get kind of immediately an error in the mean. And so what we suspect here is that we truly have a dry bias in these measurements, and that this dry bias is more than what we believe would be in the error from the temperature variability. So it's a real physical dry bias. And it's perfectly plausible, because as you said, this Lagrangian estimate removes all water, whereas in reality, some of the condensate evaporates. But that's the mean dry bias. There's another problem, which is the timescale variability. And so the thing is, if you have a volume with air in it, and you shake temperatures a little bit, and you process the air slowly through it, what is your probability to see kind of the minimum temperature? The slower you do that, the higher the probability that every parcel in that volume sees the minimum temperature. And so what we've shown here is that actually the temperature or the water mixing ratio is directly kind of more or less exponentially proportional to the time scale with which you advect your air through the coldest temperatures. And so what we found is also an artifact here, that when we use diabatic trajectories instead of the vertical wind field, we use the diabatic model heating rates. They are affected, funny enough, by the cosmic temperature assimilation. Why is that? Well, it's obviously a temperature change, so the water vapor will change. But what also happens is that for the diabatic calculation, you need a radiative transfer calculation. That depends on the temperature. And so now all of a sudden, in your reanalysis system, the temperature is getting actually warmer or higher. That means the diabatic heating rates are going down. So you have a longer residence time. And so a simple artifact comes from this temperature shift. And that's an uncertainty that may be also happening in the past, that we can't diagnose it. Here, for this 2006 event, we can diagnose it because we can see that a difference between kinematic trajectories, which use the vertical wind field, and the diabatic trajectories. So the results then, for the full time series, for the variability, after subtracting the mean annual cycle, this is the time series of all model results that we have. And what you see is what you've already seen from the temperature data. In the 80s, the discrepancy is largest. That comes simply because all these various temperature data sets are very different in the 80s. And then from about 1990 onwards, there are discrepancies, but they are generally, they see the same thing. What you see is kind of 3 points. There's kind of a massive drop in the 80s. Then you have kind of a period which is quite quiescent. You have here the Pinatubo period, but actually look, water vapor goes up before Pinatubo. Then we go in a sequence of quite regular oscillations, and we have this drop in the year 2000. This is shown here again. This is probably the most prominent thing that you see in the water vapor data. And so these are these oscillations, and this is now emerging halo and MLS data. And the black line here is the data from the observation, and the colored lines are our model estimates. And so what you see is this gray line is the uncertainty from merging the MLS data to the halo data, but there's quite some uncertainty in that. And by and large, we seem to be able to reproduce observations quite well. However, when we zoom in, we notice the following deficits. What we've done is we've done a separation into higher frequency to lower frequency. This is the higher frequency part with something up to 2 or 3 years oscillations. And then the correlation coefficient is typically around 0.9 or higher. So these oscillations are reasonably well reproduced. This is the residuals of the lower frequency variations. And what you notice here is the black line is the observation, and the colored line are the models. And so what you notice basically in here, you have a drift, and in here, you have a drift, such that initially, the models get drier in the mid-90s relative to the observations, and then here they get moister again. And so if you take a trend over the whole time period, it's actually not so bad, but we would be really pointing out, don't believe trends. You know? It's what's happening here is obviously something is compensating, and we're not quite sure what. What is also interesting is actually that if we go back here, the drop in 2000, you see this is the model calculation. You see the post-2000 values are actually about right. But all models here, they are drier than the observations before 2000. So when we actually would reproduce this picture here, we would never get as pronounced a drop here as what is observed. And this is mostly because the model starts drying already in this period here. So it's quite interesting in the sense that we do quite a good job, I would argue, in capturing the variability, but kind of the most kind of eye-catching effect, namely this 2000 drop, is actually not captured very well. And we can do the same thing for, and this is now on 10 hectopascals. As said, we're now looking higher up. We're advecting things forward with the mean age spectrum. This is the comparison again. I go fast forward. We do the same thing at high frequency versus low frequency decomposition. And we actually see the same thing against the halo. Initially, the models are too moist. Then they're drying relative to the observations in the mid-90s. And then you kind of have, again, this drop underestimated. So for the halo, it's a consistent story. What is not consistent is when we just plot the residuals against all data that we have. So there's a second satellite named the SAGE-2 satellite. And SAGE-2 is generally used for aerosol retrieval. And this is because its measurements are more sensitive to aerosol. So it's not a good water vapor retrieval. However, if you plot the residual against halo, you see again kind of these two drifts here. If you do the same thing against SAGE-2 data, you don't see a drift. So what that means in turn is that obviously the models do better what what SAGE sees, but also SAGE-2 would not have had such a pronounced drop in 2000. So the problem is now, which one do you trust? And conventional wisdom is to trust more halo because it's less susceptible to aerosol. But what we find or found out in this paper is that it's really interesting that in principle the models agree better is what you basically have or think is the worst measurement. As a second question comes back what happened in the 80s, and the problem there is we really only have the SAGE-2 that goes back to the 80s, and we have these balloon-borne measurements over Boulder. And the Boulder measurements are very scarce, only a few measurements per year, and they're over Boulder and not over the tropics, so it's an additional complication. But what we find there, this is the residual over Boulder, and what happens is around 2000, the Boulder measurements also drift relative to halo, so just to make your life even more complicated. But then the funny thing is that actually the colored lines here are different model residuals, and so you see, again, kind of in the 80s, you have large differences, which comes from these large temperature differences. So relative to the Boulder record, this kind of orange line actually does best. And that is the curve where we use the era interim temperature without any correction, so it's just out of the box. And this is the thing that people would consider least reliable. Why? Because they do least adjustment to the radial SoMAS. So the perplexing thing is, again, we kind of have the best agreement in terms of water vapor is what you believe is kind of your worst temperature data set. And so depending on which data set you take here, you either have a huge problem because you see here, this is the Haddad corrected temperature data. And for the Haddad, you see there's a large drift of the 80s relative to the 2000s. Yeah? So that would be, you would be saying there must be some missing process. However, if you think, well, maybe the interim temperatures are not so bad, then you actually have far less of a problem. And so we have basically this kind of problem that, well, we can do reasonably well, but if you zoom in and do a very detailed analysis, it doesn't exactly work. And you can't really point out where the problem is. It's not that you would have in these residuals of one model versus one observation, that all these residuals would have something in common, where you would say, yes, this is an indication I have neglected something in my model calculation. No, it's really that the residuals are basically different for each measurement and for each model run that you have. And so the question is really, do we have hard evidence that something is missing? And I think it's just we can't say it. That's a very frustrating situation. And so perhaps the last thing is, where do we go from there? Well, obviously, one good thing here is that we've now zoomed in for the first time. We have identified periods where things seem to diverge. Before that, we didn't even know. All we knew was kind of the last 50 years, somewhere things don't add up. Now we have a much better view on it. It's a few years where things drift relative to each other. So you can go back into the data and check, is there something obviously wrong? That's one thing. The other thing what is interesting is kind of, this is still a diagnostic approach. I don't have a prognostic theory. And we have a bit of a dilemma here, because what is shown here, and so we can't really, sorry about that. It's the black lines is a time versus this is longitude and this is latitude. It's again this distribution of the Lagrangian dry points. And what we've shown several years ago is, as temperature patterns change, distribution of the Lagrangian dry points also change. They follow the minima temperature. So you cannot have kind of a weighting with a given weighting function. So we know the problem is extremely complex. For some reason, if you do this Lagrangian estimate and you just relate it to tropical mean 100 hectopascal temperatures, the correlation is extremely high, it's about 0.9 or so. And the reason why that is so is coming back to the beginning. A lot of the temperature variability is strongly zonally symmetric. So the largest variability you would see both in the Lagrangian estimate and in the Eulerian perspective. Yeah? And so it's sometimes very hard to convince reviewers and other scientists that it's worth the effort. Yeah? And so what you see here is that the story is far, far more complicated than any zonal mean or kind of area mean temperature. But it's still kind of, it does a reasonable good job. And so the frustrating thing is very often kind of reviewers say, leave out this complicated thing. It's not necessary. It's all about this mean temperature, which it is not. And with that, I thank you for your attention.
Let us see if there are any questions for Stefan. Edmund, you have it?
Yeah, you spoke quite a bit about the dependence on sort of the temperature estimate, but you use one single transport in that. So how what's the sensitivity?
To a transport, yes. Yeah. So yes, the sensitivity. I mean that's a really interesting question, and the problem is, which comes again back to this prognostics here. So we've tried some attempts of also kind of, if you have an error in transport, could you predict what that means eventually for the water vapor? And that you might have kind of almost a Eulerian metric of an error in transport. And we haven't succeeded in that. So we've succeeded more or less for the temperature, but not for the transport. So for transport, the only thing that we can do is different representations of transport. And so what we used is, as I said, kind of kinematic and diabatic trajectories. So they use the same horizontal wind field, but a different kind of driver of the vertical velocity. What we found was that results are somewhat sensitive, but over the long time period not, except for this 2006 event, where we can point out that we know why the diabatic calculation all of a sudden goes different from the kinematic. So that's one thing. Then the question is, do you have other data sets? Yeah? And in the past, we have used era 40 instead of era interim. And our results are still very, very similar. They're not exactly identical. And other people have used different data sets, and they've all more or less reproduced our results. So it seems that more or less the big kind of large-scale structures are the same. What is obviously not represented would be all small-scale variability. And that is obviously at the question, can we explain it or can we not explain it? And as said, I mean, it's an uncertainty.
So there is another question.
So what determines the coldest tropopause temperature?
That's a very good question. We've even written a previous geophysics review paper on it. It's called Stefan. So what you have is you have kind of deep convection, and based on deep convection, you basically say, okay, up to about 150 millibars, the first mode or so. Everything is driven by the Morse adiabatic collapse rate. From there on, the balance of terms is, as one can also, in that picture of the diabatic terms, it's becoming more a balance between dynamical forcing and radiative heating. And we would argue that tropical tropopause is substantially below radiative equilibrium because of momentum dissipation in the stratosphere, forcing the upwelling circulation. What has been clear since 10, 15 years or so is that it's not necessarily only the extratropical waves which have been kind of promoted in the 90s. The problem is how do you force the upwelling in the tropics? And there's a lot of kind of work going on. We also do work on basically on the quasi-stationary tropical waves and the dissipation of kind of this Rossby Kelvin wave pattern in the stratosphere, forcing kind of a residual circulation that would be relatively shallow, so maybe up to about 70 millibars or so. And that this circulation is actually much stronger than what you then have afterwards, kind of the deep stratospheric branch. Kind of Alan Plump had a paper 10 years ago or so where you kind of this conceptual difference between a shallow stratospheric circulation and the deep circulation. And it's probably this shallow branch which kind of drives temperature substantially below radiative equilibrium. And I would argue that that is probably the main kind of driver. Of course, on the other hand, you have people saying overshooting convection is a very important part of the story, in the sense what you're bringing up is as soon as convection overshoots the level of neutral buoyancy, you basically have a negative potential temperature advection. So you're cooling your layer above, and that also could kind of bring things below radiative equilibrium. But my personal gut feeling would go more towards the large-scale waves.
So, thank you.
Yes, your model simulated the variability pretty well. Well, for the strong positive trend, H2O you showed in the very beginning, what process could cause those strong?
You mean for over the 50 years?
Right.
As I said, I mean, the argument here would be simply, you can't go back to the 50s to make these measurements better. So let's focus on the period when we have spaceborne data. And another thing I've shown is, even for that period, you can't make a very strong case whether you're now really, whether you capture the thing now or whether there's a problem. And so I would be very careful in saying anything about the past. What is certainly true is, also, can you trust these measurements? Yeah, it's really a very good question. And I think if I just quickly go back, what I was intrigued is from was this curve of the variability of entry mixing ratio, so it's got just a year-to-year variability, and how that character can change sort of on 5 to 10 year time scales. And so each of these time scales that people looked at was only, say, 5 to 10 years. And it's quite clear that, if you make measurements here, you get something different than when you do it here, and so on. So this character changes substantially. Of course, you can say it's quite, there are about 7 time series, so it's quite a coincidence that 7 would give a positive trend, yeah? If, on the other hand, these 7 are not evenly distributed over the time series. A lot of them are actually measuring the same interval. So if you look at how many independent random samples of these time series you have, you might be more sort of towards 2. And then you might think, well, actually, maybe, in this initial plot here, all the way back. Okay, yeah. Might be just coincidence that this period was also kind of a bump up. And maybe these absolute values are not so wrong, in the sense that what you're not seeing here is simply these points that go back down. So you don't know. But then obviously, I mean, just a quick come back, what could cause something like that? Obviously, the very obvious thing is what affects kind of how much water you can remove with aerosol. And so if you would have just a little trend in basically aerosol property at the stratus or tropopause, you probably make kind of smaller drops or smaller ice crystals. They would fall a little bit less. So in this conceptual picture, you would remove a little bit less water. And so we can easily produce trends as soon as we are allowed to tweak the aerosol population. Yeah? But we don't want to do that because we kind of want to prove that that would be the residual, yeah? that you need it. Yeah? But it's very simple to do.
So there are no more questions, so let us thank our speaker.